The topic of our presentation is using ultrasound for electric power reliability. And this is a presentation I've given a few times for EPRA, which is the Electrical Power Reliability Alliance, a really important group that I'm a director of, which is focused on creating knowledge bases for improving the reliability of electrical assets, and it's EPRA is their coin, and I'm doing a little plug for that because it is a nonprofit alliance, and I think it's a really important topic for us. Unreliable electric power systems, they not only cost millions of dollars in downtime and repairs, but they have the potential to maim and kill us. So reliability leadership has to focus on the preservation of both physical and human assets because, well, let's face it, everyone has the right to a safe work environment and to return home unharmed at the end of the day. SDT Ultrasound Solutions, we are the world's favorite ultrasound company, and we measure that not just by the vast number of ultrasound instruments that we put into the marketplace each year, but by the quality, the endurance, and the sustainability of the condition monitoring programs that we help our customers to implement. We've been in business for around 50 years, and in that half century, we've expanded our market to cover 5 continents and around 70 countries. So if you live in a part of the world where you could purchase a Coca-Cola, then you have access to SDT Ultrasound Solutions. Our mission is simple. We want to provide solutions that help you to anticipate failures, to help you control your energy costs, and to help you improve the product quality while contributing to the overall reliability of your assets. And our values are what propel us forward. And when the driving becomes difficult, it's gut check time. And if my decisions can check the boxes around respect, simplicity, and flexibility, then I know I've made the right ones for myself, for my partners, and also for my customers, most importantly. I'm coming to you today live from Cobourg, Ontario, Canada. It's my home and it's beautiful. And one day, if you get a chance to visit it, I highly recommend it to come and see it for yourself. Our headquarters and our manufacturing and our research and development are all done in Brussels, Belgium. That's the wonderful capital city of Europe. And if you don't make it to Cobourg, well, Brussels isn't a bad pit stop either. In either instance, we're welcoming you with our arms wide open. We also have a regional office in Kolkata, India. And this marvelous city is famous for its incredible food, its color, and of course, ultrasound from SDT, the world's favorite ultrasound company. This presentation is also part of our Ultrasound Beyond the Essentials webinar series. In this regular series, we run it monthly, features speakers and topics centered around condition monitoring and reliability. The series has 3 aims: sustainability, safety, and uptime. So through Ultrasound Beyond the Essentials, we imagine a world where all the things that we need are made sustainably, and where the only impact on the planet's environment is a positive one. We imagine a world where people can work safely without stress, without pressure, without the fear of getting injured or killed on the job. And that's a reality, sadly, for too many. And we imagine a world where every maintenance intervention on an asset is planned. Tasks get executed effectively, on time, on budget, and they always follow a standard operating procedure because that is how you reduce these workplace accidents. My name's Allan Rienstra, and I am the Director of International Business Development for SDT. And in my career, as Randy said, it's ultrasound, and that's all I've ever done. And after 30 years, I don't see myself changing that anytime soon. My passion for ultrasound currently is going through a bit of a transformation. So I accept my years of discovery are probably mostly behind me. I don't do the field work anymore. But now I'm putting my accumulated knowledge to work helping people get the most from a technology that's largely under the radar, to be honest, but it helps create that culture of reliability that seems so elusive to so many of us. So today, we're going to explore how ultrasound is applied to the reliability of electrical assets. And we're going to look at what is ultrasound, just 30,000, 50, 100,000 foot level. We're going to look at what is ultrasound from the top of the highest mountain in the world. What is partial discharge? And what are the consequences of partial discharge? And what are the risks of partial discharge if we don't do anything about it when we find it? And how does ultrasound help in this? And then finally, some stories from the field. And I think these are the most interesting ones because these are authentic wins that customers have found using this important technology. Okay, so in the world of acoustics, there's 3 classifications of sound, and these classifications can be described either scientifically or by their characteristics. Infrasound, which encapsulates all the sound waves that are below the limit of human hearing. Audible sound, which references sound waves that are perceptible to us as humans. And then ultrasound, which categorizes all the sound waves above the human limit of hearing. Now, for the purpose of condition monitoring, understanding how the characteristics of sound contrast at different frequencies is the most important thing. There are 3 qualities that make ultrasound very useful for inspecting, detecting, measuring, trending, and analyzing the health of physical assets in our industry so that we can act on that knowledge. The first one is distance. So distance describes how far ultrasound can transport itself through its medium before it gets exhausted. And by exhausted, I mean, we can't hear it anymore, or our ultrasound equipment can't hear it anymore. Another word would be attenuated. Directionality is the second one, and that defines how wide a sound will spread through its medium. And how wide it spreads through a medium is really a function of how powerful the sound is. And the higher in the frequency range, the less power there is. So the air molecules, if that's our medium, tend to narrow it in and focus it in. And then the third is penetrating power. And that depicts the ability of sound to cross boundaries. I like to say that ultrasound is introverted. It doesn't like to go out and party and hang around with its friends. It just wants to stay home and chill. And so the higher you go in the frequency, the less tendency there is for sound to move, say, from air to water, or from steel to copper, or from copper to brass, or from brass back into the air. That's the penetrating power. And that's an important thing for inspectors to understand as well. We also like to say that ultrasound owns the apex of the P to F curve. And that's the potential for an asset to fail curve. And that means that of the big 5 condition monitoring technologies available to most reliability departments, ultrasound gives the earliest indication of an asset's deteriorating condition. Now, did I say that ultrasound is better than the other condition monitoring technologies? No, I did not say that, and I will not say that. I said it's first. And in the world of planning, scheduling, time-based task execution, being first is a huge advantage. But all of these technologies, I consider them to be complementary to each other. Ultrasound detectors work by mixing high frequency signals with low frequency signals. Our circuitry then takes the sum and the difference of the signals, and it results in the conversion of ultrasound to audible sound. All the while, the characteristics and qualities of the original sound are preserved. And this principle is called heterodyning. Inspectors now have superhuman hearing capabilities, and they're able to anticipate defects much earlier than otherwise would have been possible. With our newfound superhuman hearing capabilities, there comes a tendency to try and do everything with ultrasound. And here we have to be careful to understand what is possible and what is not. So knowing which defects can be discovered with ultrasound can save a lot of time and frustration, because there's no point in using the wrong technology on the wrong application. Ultrasound allows us to hear above the noise of the factory floor and over great distances. By screening out low frequency sounds, inspectors can hear sounds that are consistent with machine and asset system defects. And these defects produce ultrasound from 3 phenomena: friction, impacting, and of course, turbulence. So when in doubt where to use ultrasound, ask yourself, if the defect you seek produces friction impacting or turbulence, then it's a fit for ultrasound. So based on this fit principle, we at SDT identified 8 primary areas where ultrasound is particularly useful, and we call them the 8 application pillars. And they are mechanical defects in any mechanical system, leaks, so we can find pressure and vacuum leaks in high noise conditions, lubrication. We can use the technology to avoid over and under lubrication of motor bearings, to grease bearings right. We're going to talk about electrical today, inspecting medium and high voltage systems for arcing, tracking, and corona. Valves, assessing valve tightness and function. And of course, steam systems, that's number 6, finding faulty steam traps and components. Pillar number 8 is hydraulics. So we can troubleshoot any hydraulic system for passing, for blockages, and then finally, tightness. Determine the tightness of any volume. But today we're going to focus on the electrical application pillar. That's that one right there in the middle. But if in a holistic ultrasound program, if you can get all of these together, we have 0 waste, we have 0 accidents, and we have 0 downtime. And that fits so beautifully with our sustainability and our safety and our uptime vision for ultrasound beyond the essentials. So what is partial discharge? Partial discharge is a localized electrical discharge or spark in an insulation system that doesn't completely bridge the gap between 2 conducting electrodes. It can occur at any point in the insulation system where the electrical field strength exceeds the breakdown strength of that portion of the insulating material. And this could be due to voids within a solid insulation material. It could be across the surface of insulating material. It could be in these gas bubbles that you see here within liquid insulation, or around electronic gas in the form of corona. Partial discharge is an atomic reaction which, due to the movement of electrons, ionizes the air molecules at locations of high stress. So this ionization splits the oxygen molecule and allows to form ozone and nitrous oxide, which in their normal states are generally harmless. But when you mix them with water vapor, they become corrosive. And if you've ever walked into a substation and you notice that smell of ozone, then you've witnessed firsthand the presence of partial discharge. Internal discharges exist beneath the surface of these components. Partial discharge has many causes, including, as I said, voids in solid insulation, often caused during manufacturing defects, mechanical breakdown or damage due to insulation, sometimes caused by installation or poor workmanship. Design defects such as poor stress control or irregularities, or a combination of factors that are characteristic of assets getting older and just breaking down. Partial discharge emits energy in a number of different ways, producing electromagnetic emissions in the form of radio waves, light waves and heat, acoustic emission in the audible and the ultrasonic ranges, and then again, ozone and nitrous oxide gases, which are corrosive. These sonic emissions are what we focus on with ultrasound, and they enable us to detect, locate, measure, and analyze PD activity so we can identify faults before they develop into failures. Now, partial discharge activity can be intermittent. It's not always going to be there, and that can be frustrating to inspect. Or it can vary with intensity over time as well. Once it starts, the damage is always going to get worse, never better. Where do we find PD? Well, the answer is anywhere and everywhere. You can find partial discharge activity in all types of high voltage, medium voltage, and even low voltage power assets. From switchgear, motor circuit controllers, to transformers, overhead power lines, even underground cables. And we'll see that in some of the case studies I'm going to share with you at the end of the presentation. Partial discharge causes degradation and failures. And experience shows that PD activity is a contributory factor in over 80% of disruptive substation failures. It is the most reliable indicator of the true condition of insulation in live assets. So why do we want to test for it? Well, any discussion about risk first has to include health and safety. That's first and foremost in my life, and it should be in your life. But it shouldn't ignore asset reliability either. One certainty is that safety and reliability risks are both linked to unscheduled downtime, to costly legal exercises, and ultimately lost profit. Now, a winning solution is going to identify safety and reliability as one and the same, and they are one and the same, and marginalizes their impact to the other three. So that is why we test for it. Now, the consequences of allowing partial discharge to progress include damage to assets, pole fires, explosions, and deadly arc flash. And as I said at the opening, unreliable assets not only cost millions in downtime and repairs, they possess the potential to maim and to kill our colleagues. So ultrasound presents kind of a triple win solution. It reduces the risk of arc flash exposure. It ensures that equipment reliability, and it also allows inspectors to work at a safe distance from high voltages. And this video that we're playing now, that's just a dummy. That's not a real human being, thank goodness. But you know, there's tons and tons of information on the web about the dangers of arc flash and arc blast. And if you haven't read about them, then you need to be aware of them and the safety precautions that need to be in place for all of the inspections you do. One of the things I love about ultrasound is that we're always on the safe side of the fence. Notice in all these photos that I'm showing you right now, that the inspector is in high voltage situations on the safe side of the fence, a safe distance away. Ultrasound detects defects which, when left to deteriorate, could lead to an arc flash event. And this doesn't suggest that ultrasound removes the need for personal protective equipment and other safety measures. I've yet to meet an arc flash suit which can detect an arc flash at its inception. But if you're wearing an arc flash suit as your last line of defense, ultrasound should be your first line of defense. So what we're showing here essentially is what it would look like on this three-phase transformer if our inspector over here is at a safe distance away. You can see the red dot, and that red dot is coming from this parabolic antenna. This parabolic sensor, remember I said ultrasound is directional. What the parabolic does is it makes it even more directional. So we know that there's corona or partial discharge activity on one of these three phases. And by using his laser sight from a safe distance away, we're we're enabled to pinpoint exactly which one is the troublemaker. Now, how great is it to be able to inspect motor circuit control panels without the risk of opening them up and exposing technicians to the possibility of an arc flash event. Now, and I'm not saying anything derogatory or taking away from infrared technology. There's lots of great ways that we can use infrared technology safely using IR windows and whatnot. But just imagine that you could pick up an ultrasound gun or device or meter as our inspector is doing here, and anywhere where there's an air gap around the door, a vent, here's some vents, we're going around the outside of the door. These panels are not hermetically sealed. And so any air gap is an opportunity for ultrasound to go from inside to outside. It will travel through the steel, but remember, it's introverted. It wants to stay in the cabinet and just chill. but we can hear it through those seals, through those those gaps in the seals. Now, when we come across a panel that is hermetically sealed, what we do is we simply place a contact ultrasound sensor with a magnet directly on the cabinet's outer panel. And now any ultrasound that's inside that panel is going to do one of a couple things. Some of it's going to hit the panel and reflect back in. Some of it's going to be absorbed by the steel panel, and some of it's going to pass through the steel panel and into our sensor, allowing our inspector to hear. Just think about when you go to visit your doctor and the doctor puts a stethoscope on your chest and listens to your heart. Well, this is exactly the same concept, exactly the same principle. Okay, so that's a real high view of what ultrasound is and how it's effective for finding these different sources of partial discharge. Now what I want to do is I want to share with you I don't know how much time we have left, but I'm sure Randy will stop me when I run out. I'm going to share with you a few stories that we've gathered from the field. And one of my best resources for these is a really good friend of mine. And that's one thing I love about being in the business for 30 years is over all of these transactions that we've done, I've pulled in a lot of friends and people that I have common interests in outside of ultrasound and outside of reliability. Craig and I are avid cyclers, so we're always chirping each other about who can ride their bikes the furthest. But Craig is also a seasoned field technician with over 20 years of field work with both with ultraviolet cameras, with infrared thermography. He uses the SDT equipment, the SDT 270 and the 340, and he also uses this SonoView. I'm not sure if it's visible, but the SonoView. I'm going to talk a little bit about this acoustic imaging camera as well. Craig uses all of these technologies, and he's had some fantastic wins over his 2 decades. He's also a frequent presenter on our webinar series. What you're looking at right here is again, just a 3-phase transformer. And what we were able to, what Craig was able to pick up was partial discharge activity, not at this one, but at this one. You can see a bit of the white nitrous building up around there. And there was no heat signature from this. He opened it up and he was looking at it with his infrared camera and he heard nothing but clear as a bell. He heard partial discharge from in the ultrasonic range. And what that tells us is that, again, the symptoms of partial discharge are sometimes intermittent, which means that sometimes you can see them with an infrared camera or an ultraviolet camera, and sometimes you can hear them with an ultrasound camera. And so if I go back to those condition monitoring technologies, and I'm saying, well, ultrasound might be first, but that doesn't mean it's the best. They're all complementary. And in this particular case, ultrasound revealed the problem the earliest. Now here's something that you'll see in industry a lot. This is a high voltage cable. There's 2 high voltage cables. And again, this is a classic case of what I call poor workmanship or carelessness, where these 2 high voltage cables were installed and allowed to be in contact or in too close a proximity. And over time, you get a little bit of a bird caging effect, or you get an insulation breakdown in the outer sheath of that cable. And then you start to see that little bit of white build up there. Again, no heat, but lots and lots of corona discharge. And so this was, again, something that Craig was able to detect with his SDT 340. Now here, okay, another situation, another transformer, and each of these phases are shielded from each other with a mica board. But that's only good if you make sure that the cable isn't touching the mica board. But as you can see here, with his, he uses a FLIR, a fairly new FLIR camera. This FLIR camera was able to pick up a considerable heat signature here, and there was also partial discharge activity. So this was something that was detected both audibly, ultrasonically, sorry, not audibly, ultrasonically and with his infrared thermography camera. And again, here's another one. Now, this one did not produce any ultrasound for one reason or another, but he was able to see significant heat buildup in this transformer. So again, complementing each technology and arriving at some kind of a outcome that can be shared with the planner so that the maintenance on this asset is done on our terms, not the asset's terms. When we wait for the asset to dictate, then we're running around scrambling for parts, we're running around scrambling for labor, and everybody is in reactive firefighting mode. And what happens? Somebody gets hurt. That is when most accidents occur, is when we're running around doing things without a plan, without a standard operating procedure, when we're trying to be heroes. Okay, I said I'd talk a little bit about the acoustic imaging camera, the SonoView. This is Craig, and we're looking at some transformers again. I'm just going to run this video. I don't think there's any audio for it, but what's Craig's doing? And pardon me for the winter scene. This was last winter. I'm not really too excited about showing snowflakes right now, but got to work with what we've got. So Craig is scanning the transformers, and now he's looking up here at these where these three leads are coming through the concrete block wall. He's recorded an image. You can record an image, or you can record a video with the SonoView. So what the SonoView does is it has 112 digital ultrasonic MEMS sensors. And these MEMS sensors will pick up sources of airborne ultrasound from as much as 150 meters away. It's quite an incredible tool. But then what it does is when it hears the ultrasound, it also has a camera on it, so a visual camera. So on the backside, the inspector is able to look at the screen, just as Craig is doing here in the picture. And if there is any source of partial discharge, it will show up as an overlay where it is. So we're able to hear it, we're able to see it, and we're able to imagine exactly where it's coming from on the asset. So when we froze this and took a picture, what Craig found was that there was a partial discharge occurring right at this termination point, right at the brick wall here. And this is, he said, it's quite common. He finds a lot of situations, I guess, where anywhere where you're moving through a wall like that, that's a tendency because the buildings resonate, they vibrate, and over time that breaks down that insulation, and you're going to have partial discharge there. So it's kind of this is a brand new technology. It's got a bit of a sex appeal to it, and because you can see and hear, it's marrying the two senses together. It's kind of cool. Okay, this is the last one, and then we're going to have question time. This is my favorite story. I always like to save the best for last. So again, this is one of Craig's jobs. Craig lives in Erie, Pennsylvania, but he was called out to the Dakotas. So he jumped in his car and he went for a road trip. I miss road tripping. Damn you, damn you, COVID. But I sure do miss grabbing a bag of chips and just getting behind the wheel and driving. But he got to drive out to the Dakotas, to this dam here, and what they were doing is they had a generator core that they took out of service, and then they were rebuilding it. So this is a test module that was used to fire up the core, and you can see this red behind. And I think it was something like 12 meters in diameter. It's huge, absolutely huge, this generator core. So you can see bits of it here. And then above, this is the ceiling. So it was so big that they had to build a platform to access the lower level and the upper level. And then, so what this test machine does here is it powers the core, so it can go through a series of stress tests before it's put back into service. Because obviously you can see by the size of it, we're talking about implications of millions of dollars if something goes wrong. But once this thing is reinstalled, it's basically going to be back in service, hopefully for 50 years of trouble-free trouble-free life. So here's a close-up of it from below the floor. Pardon me if I'm looking at my slides here, but just to give you a sense for how large and how complex this generator core was. And here's another image of the same core, but now we're on top. So this is the top half of it. I'll just back up one slide. There's the bottom half, and there's the top half, and this floor is a platform in between. And so using, he had his infrared camera with him, he had his ultrasound with him, and he had his sonoview with him. Using his sonoview, and he just stood in the middle and just did a 360-degree scan around. And right here, he picked up something very small. Well, it wasn't that small. It was 52.7 decibels. So it was a significant event. And it was enough for him to say, no, not yet. That can't go into service. We got to find out what's causing that partial discharge. And so they shut down the voltage core so that they could safely inspect. And they found a piece of welding core. So this is just a piece of welding rod that had been dropped or discarded by one of the technicians during the recommissioning, during the rebuilding of it. And it just goes to show how small a problem like a piece of welding rod could have the potential for a seven-figure failure on something that and by doing the proper test procedures, you can save you and your customer a lot of money for sure. And I know Craig was well compensated for this job, and it looks like he earned his keep on that particular day. Okay, I guess it wasn't the best for last. Here's one more here. This is a 13.8 kV switchgear yard, and again, this is just a cable running from the transformer over to an insulator, and we got some bird caging going on right here. And that breakdown of the insulation is producing just a source of airborne corona, which we were able to pick up. We could pick it up with our parabolic dish. We could pick it up with the sonoview. We could not pick it up with infrared because there was no heat generated. Corona discharge does not typically generate any heat. Now, what you see here on the screen, this is a little bar graph. This is a bar graph called PRPD, which is an acronym for phase resolved partial discharge. And this allows us to analyze the source of the corona at 360 degrees so all phases of the sine wave. So we can see, and by looking at the patterns through those 360 degrees, we can look at the patterns and determine whether it's a surface discharge, a floating discharge, or whether it's corona or some other effect. And so this is a new analysis tool that we have. Okay, there's one more. Craig calls this one the one that got away, and this is just a polyceramic insulator, and he was supposed to inspect it, and he missed it. And when he missed it, it caught on fire. And when it caught on fire, it shut down a transformer, and it took his customer out for the better part of 3 days. And that's a manufacturing facility. That was 3 days without being able to run key processes. Okay, bad enough, this customer couldn't make their widgets. Imagine if it was a hospital. Imagine if it was electrical assets powering an ICU ward. It just goes to show you that when an electrical asset fails and you're in the vicinity, you have the risk of being injured or worse. But what about the people that are lying in hospital beds, relying on that power? Boy, reliability is so critical. And we have to think beyond just our ability to make widgets. Because it's important to make widgets, but it's more important to keep our hospitals running and keep them safe. We can find corona on a lightning arrestor with the sonoview, with ultrasound. And we can have a little demonstration there. So here's my parabolic dish. I've got my laser. and I can point it. And this is my ultrasound detector over here. And when I find some corona, I take a measurement. And I can see a time waveform. The audio is very low on this, I apologize. Here we have another pole. And we just scan, we scan, we scan, we scan, we scan. It's here somewhere. Where is it? Where is it? Oh, there it is. There we go. We can have transformers on a pole. Here. There it is. Last one, I think. No, we already know it's over here, right? And again, each one of these time waveforms can also be looked at in the spectral view. And in the spectral view, it allows us to see, what we'll see here in North America is we'll see peaks every 60 hertz, which are the line frequency. And if we're over in Europe or other countries, we'll see those same peaks, but we'll see them at 50 hertz. And it helps us to determine whether the problem that we found is related to corona, or whether it's arcing, or whether it's tracking. And being able to do some deeper analysis and deeper assessment allows our planners to decide on the scheduled maintenance, what kind of maintenance they're going to have to do. A lot of times with corona discharge, it's a matter of just getting the dry ice out and cleaning it and restoring it. Okay. I'm going to end things there, Randy, with my message of safety and reliability, and tying both of those important concepts back to ultrasound. And so if we've got questions,
we do.
I'm here to answer them. And if not,
okay, the first question is that's come up is it possible to use this technology on electrical underground cables to detect faults? Examples: phase-to-phase cable faults, phase-to-ground faults, and insulation failures.
No. Underground is not going to be so easy, just because the types of defects that we're looking for here are caused by, remember, friction impacting or turbulence. In this case, turbulent flow, and that turbulence typically needs to flow through the air.
Okay. How can we compare SonaView to the recent Fluke II900 acoustic camera?
Well, you can compare it in a number of ways. I have a whole presentation in a webinar series dedicated to comparing those two technologies. I mean, from a specification point of view, we have, there's many more sensors on the, we have 112 sensors versus 64 sensors on the Fluke. Okay. So the II900 in field tests doesn't have the range and sensitivity that SonaView tends to have. So we tend to be able to hear defects from further distance, which to me is important. I'm looking out my window here, and there's some 600 kV lines that are coming off of the Darlington and Pickering nuclear plants here near Toronto. And I know that those are around 200 feet in the air. And so it's important to have that range of distance. Weight is another one. So the SonaView is the lightest, most compact device on the market. It's about a pound to a pound and a half less. And that doesn't sound like a whole lot, you know, if you're pumping iron all day, but if you're above your head like this all day, it actually starts to weigh on your shoulders a little bit. So those are two real big ones. Price point. We see price point for the Fluke device all over the place, depending on which country you're in. I've seen it sub $20,000. I've seen it at $30,000. So price point, ours is around $18,500, and we sort of hold the prices pretty steady. Then I would say that the other real significant feature would be a product that we call Insights. And Insights is something that allows us to, let me just see if I can bring it up. So Insights is a reporting software that we have. Can you see that on my screen?
Yep.
So Insights allows us to generate compressed air leak reports, to generate electrical reports, and then so let me see if I can find an electrical report here. Here's an electrical report. And so what I do with the SonoView is using a USB drive, I import my images that I've saved from my field inspection into Insights. And then I very quickly just gather them all up in one click, and I have a report. So here's a report of every problem that I would have found on this electrical. So the image is there, the metadata from the camera is there, and then I have the ability to add in notes. So if I just pop back from there, I can go in and I can add in, the location, tower 10 east side. And then I could just say, it was a humid day, and I was 30 meters away from the leak, or from the, I can add different notes in here. I can save those, and then those get added into the report, so I can share that with my planner. And then when they eventually get fixed, we can just click off that it was repaired. So the reporting software is a real big feature for us, and it's a real powerful tool that allows collaboration across the department. Right?
Can we quantify PD activity by SonoView, or only detection is possible?
Quantifying.
Can we quantity? I don't know, maybe quantify.
Yeah, I understand.
PD activity, yeah.
How do you quantify something? You want to quantify it in terms of loss? Do you want to quantify it in terms of how much? I don't think you can quantify it so much as you can trend it from 1 week to the next, or one month to the next, to see if it's getting worse. It's going to get worse anyways, but and if you're going to do that, then there's a few things that you have to take into account. And the biggest one is what we call the inverse distance law, which is the distance that we are. If I'm 10 meters from the source of the problem, I'm going to read X decibels in terms of how loud it is. If I move myself 20 meters away, and in other words, I double my distance, my decibels will halve. Yeah. And so it's important to know what variables you need to trend.
Right. Okay, here's another one. What is the voltage threshold above which ultrasound becomes useful? I
can detect arcing in a 110 volt light switch. So it's really, but corona, in terms of partial discharge, it's a broad term that talks about corona. It encompasses arcing and tracking and all of these problems. Arcing can occur at very low voltages. Corona only occurs, I believe it's, I want to say 2000 volts, and I'm sure that there's somebody on here that's smarter than me that's going to correct me. But there is a threshold for corona where above a certain voltage you can hear it, and below it, it just doesn't exist ultrasonically.
Okay. Next question. Do you have a solution for localization of internal partial discharge in power transformers?
No, I'm going to say that there's better technology for that than an airborne detector. Now, we did show an image on where we put a magnetic type sensor onto a circuit panel, and we can put that same sensor on an oil filled transformer, and we can hear partial discharge inside, because it uses the oil as the medium to move it from its source inside to the outer shell of the transformer. But I honestly, I got to say that there's got to be better technologies for pinpointing exactly where it is inside the transformer.
Okay. Is the software free with the unit purchase?
The Insight software is in its current state is free. We have a premium version that we have planned for next year, and customers will always have options for the free version, but there will be a premium version in the future. But right now it's free.
Right.
Definitely, there will always be a free version.
Okay. Can you mount the unit in the panel for how long? Can you mount in the panel for how long?
Yeah, so we have at SDT, we have a different solution for mounting inside the panel, and it's a product called Vigilant. And Vigilant connects up with airborne ultrasound sensors. And these airborne ultrasound sensors, they heterodyne the signal right on the sensor. So they provide either a 4 to 20 milliamp or a 1 to 10 volt output. And that sensor can be mounted permanently inside of an MCC panel, and then monitored using any, a PLC or any other kind of common measurement device, or you can plug them into our Vigilant. In our Vigilant, then you have a dashboard of where you can see all of the potential for partial discharge activity.
Okay. Do you have a way to log data from the sensors mounted inside the panels?
Yeah, through the Vigilant.
Okay. All right. That was the last question. Okay. Well, thanks
Awesome.
very much, Alan. That was great presentation.